All right, this is video for geometry, and you'll use this video. It's going to be probably fairly long, but you'll use it for assignment 14 and assignment 15. It sort of goes over a whole bunch of stuff about circles, and I'm going to try to go through it sort of quickly. I will send out some other videos with some problems worked out and stuff just to help you with those. But this is just basic concepts about circle, and I'm trying to squeeze it in here at the end. So that's what this video is, and a lot of stuff in here. The assignment 14 will deal with angles related to circles. Assignment 15 will deal with some of the terms and everything. There'll be probably a short quiz over that. And then it'll also deal with segments related to circles. So I'm trying to squeeze all of the information into this one video, and then you can use it to help you with both assignments. My suggestion would be on Moodle, there's a set of notes that you could print off that has all of this stuff that I'm getting ready to go over on it, and you could jot things down on there if you wanted, or just have it to show you the formulas and different things. So that might be a good idea to print that off or save it to your computer or something if you can. So going through this, just some quick terms, definitions and stuff dealing with circles. A circle has a center point. It's always got a center point. When we name a circle, we name it, this is the symbol for a circle, a little circle with a dot in the middle of it, and we name it with that one letter that represents that center point. So this would be circle P. A circle is also always 360 degrees, so all the way around the circle is always 360 degrees. From the center point to the edge of the circle is called a radius. All the way across the circle going through the center is called a diameter. The diameter is always equal to 2 times the radius, or another way to write that is the diameter divided by 2 equals the radius. So diameter is double the radius is half the diameter. If you go from one side of a circle to the other side, but you don't go through the center point, well, I shouldn't say that. If you go from one side of a circle to the other side, and the 2 endpoints of a segment are on the circle, that's called a chord. And I sort of said it wrong because when I go from this point to this point, that diameter is also a chord. Just happens to be that the diameter is the longest chord. Diameter is always the longest possible chord in a circle. But a chord is just it could be anything. It could go from here to there. It's just a segment whose endpoints are on the edge of the circle. So that's a chord. And again, you could follow along on those notes. So basically, there's a little difference here and there, but most of them are basically the same as what I have up here, what I'm showing you on this video. An arc is part of the edge of the circle. So that right there would be arc, and it's the arc symbol is this is just a little arc, and we'd name it arc PQ. Usually you name arcs with 2 letters, but that's if it's a minor arc. The reason for that is if I wanted an arc to go from let's say we wanted to go, if I erase all this, if I wanted to go from P through Q and all the way around to R, so I wanted to name that arc right there, I don't want to name it arc PR because that looks like it'd be that arc. So we don't want that. So when it's a minor arc, it's always less than 180 degrees. When it's a major arc, like this one, that means it's going to be more than 180 degrees. And we use 3 letters to name it. So this one, if I'm starting at P, going through Q, and I want to get to R, that's where I want to end up at, we name the arc PQR. So some arcs are named with 2 letters, some arcs are named with 3 letters, because we have a direction that we want to go to make sure that whoever looks at it next is going around the circle this way and not taking the shortcut going this way. So major arcs, more than 180 degrees, minor arcs, less than 180 degrees, and minor arcs use 2 letters to name them, major arcs use 3 letters to name them. A semicircle is an arc that is exactly 180 degrees. To have a semicircle, anytime you have a diameter in a circle, if I draw any diameter in any circle, this side over here is a semicircle, this side over here is a semicircle. So a diameter splits a circle in half, and when you split that circle in half, each of those halves is called a semicircle. When we have a semicircle, we use 3 letters to name it, just like we would with a major arc. Circumference of a circle, the distance around the edge of the circle. There's 2 different formulas. You can use either one you want. Sometimes it's easier to use the first one, sometimes it's easier to use the second one. They're both exactly the same formula. Just the first one uses diameter, second one uses radius. So if you know the radius of the circle, then maybe you want to use the second one. If you know the diameter of the circle, then maybe you want to use this one. Either one of them, it's going to give you the distance around the circle. It's diameter times pi, or 2 times radius times pi. Diameter equals 2 times the radius. We said that on the other page, so that's why either one of those formulas work. A lot of times when we're doing this stuff, especially if you're doing like the ACT test or something, pi is 3.14 whatever. A lot of times we'll just leave it in terms of pi. So if we know that this diameter right here is 17 centimeters, a lot of times we'll just write the answer for the circumference as 17 times pi centimeters, because that's an exact answer, instead of rounding pi off to 3.14 and giving a rounded off answer. Sort of the same thing that we talked about when we talked about the square roots, and you leave something as square root of 3, so you give an exact answer. Same idea here with pi. A lot of times you'll just leave the number in terms of pi instead of punch it into your calculator or whatever else. We're not going to do a whole lot with this, so it's not going to be a big deal which way you do it, but just know that that's the case a lot of times. A lot of times you just leave it that way because you want an exact answer. Area of a circle, formula for area of a circle is pi times radius squared. We talked about that earlier this year. Pi times radius squared, so we just take the radius and square it. So if this radius is 8, you got to be careful when you do this, because 8 squared is not 16. All right, it's not the same as the diameter, same as going all the way across here. It's 8 squared, so it's 64. And if we wanted to give that answer, again, if we wanted to leave it in terms of pi, we would just say 64 pi, instead of grabbing our calculator and writing out or rounding off the answer and making pi 3.14 or whatever. Formulas for circle. This is the standard form for formula for a circle. Just like you had forms for lines. You had y equals mx plus b and stuff. That was a form for a line, or an equation for a... The equation of a circle looks like this. X minus h in parentheses squared plus y minus k squared equals r squared, where r is the radius, and h and k, these two, are the center point on the circle. If the center point happens to be, if we're on a graph, and the center point of the circle happens to be the origin, 0, 0, then your formula just looks something like x squared plus y squared equals, and then maybe the radius from here to here, maybe it's 5. So that'd be 5 squared over here, or 25. So the equation would look something like that. X squared plus y squared equals 25. If the center point is not right at the origin, so maybe your circle is over here somewhere, and your center point's like here, the coordinates of that point right there are h and k. So if I had a circle, I'm going to erase some of this. If I had a circle and it was here, and I knew that center point was 3, 3, and I knew maybe even if I touched it down here, I could find the radius right there, and that radius is going up 3, so the radius is 3. Then when I write this equation, all it is x minus our x coordinate right here, that's your h. So x minus 3 squared plus, this is your k, y minus 3 squared. They're not always going to be 3, of course. I just made this one, tried to make it easy on myself. And then the radius, well, we figured out the radius right here. That distance from there to there is 3. So it'd be 3 squared or 9. So the equation of this circle would look like x minus 3 squared plus y minus 3 squared equals 9. That's the equation of that circle. So if you're given something that looks like this, you can find the radius and the center point of the circle. The center point of the circle is just going to come from here and here. Here it's x minus 5, so the x coordinate is just going to be a positive 5. Here it's y plus 4, so we change this sign. Instead of a minus, it's a plus in there. So that means the y coordinate has to be the opposite of that, which would be a negative 4. That's your center point. And then your radius, the length of your radius, we look at this right here, and remember that's r squared, so we just take the square root of this. Square root of 100 is 10. So we know where the center of that circle is and what the radius is. And again, a lot of the homework's not going to deal with any of this stuff, but it's stuff that I wanted to get through and give you some idea, a little idea. So when you see it later on in other math classes, hopefully you'll remember just a little bit of it. A couple other terms, a secant line. A secant line is a line that goes through a circle and touches the circle at 2 points. That's a secant line. Goes all the way through the circle, touches it at 2 points. A tangent line is a line that touches a circle at exactly 1 point. So it sort of lays on the edge of the circle. That point where it touches it is called the point of tangency. That's going to be important to a couple of things that we do here in a little while. So secant goes through the circle. Part of that secant is always a chord. Goes from here to here. That segment from there to there would be a chord. So it goes all the way through. A tangent just lays on the edge of the circle, touches it at exactly 1 point. An inscribed polygon, we talked about inscribed earlier this year. Inscribed means inside. So if you take a polygon and you inscribe it in a circle, all the corners of that polygon are touching the edge of the circle. A circumscribed polygon would be a polygon that touches the outer edge of the circle, and it's got to touch each side of the polygon, has to touch the circle exactly once. So each of these sides of the polygon are tangents to the circle. Don't get this, I should have said this on the last slide. Don't get tangent of a circle confused with sine, cosine, and tangent. Two completely different things. All right, so this is tangent of a circle. Sine, cosine, and tangent are trig ratios. Don't get them confused. Sector of a circle is like a piece of the pie. So if we want just a sector of a circle, you want a section of that circle. So it's almost a triangle, but it's got this rounded edge. That's a sector of a circle. Now, this is the important stuff. This is what the assignment's going to be over, and it's not real difficult. And there's one page on here that's a major thing that will have all the rules, and if you use that one page, you should be able to do all this. Dealing with circles and angles. So angles related to circles. The first one, and probably the easiest one, is a central angle. And it's called a central angle because its vertex is at the center point. So the vertex of the angle is at the center of the circle. It's got to be right at that exact center point. When we have that, this angle cuts off, and all of these are going to do sort of the same thing. It cuts off this arc of the circle. The measure of that arc, how many degrees that arc is the same as the measure of that angle in the circle. So if that angle is 120 degrees, the measure of this arc out here is 120 degrees. And since we know that a whole circle is 360, that means this arc going from there to there would have to be 240 degrees. And that's all stuff that we can find. But a central angle, probably the easiest one, vertex is at the center. If this angle is 50 degrees, then this arc right here that it cuts off of the circle has to be 50 degrees. The angle and the arc have to be the same. If we have this, and we have this angle, and we know that this arc is 80 degrees, then this angle has to be 80 degrees. That's if its vertex is at the center. So if the vertex of the angle, if the where the angle, the point where the two sides come together, if the vertex is at the center, then the arc and the angle are the same. An inscribed angle, I know these look a little different than your notes. There's another slide on here that's going to look the same as your notes. So if you just follow along, you'll start to understand. An inscribed angle has its vertex on the circle. And then it goes, the angle is inside the circle. But the vertex has to be on the edge of the circle. Whenever you have an inscribed angle, it cuts off an arc right here. Just look at the side there where it cuts off that arc. And the angle and the arc are still related, but they're not the same like a central angle. The arc is always going to be 2 times the angle. So if I know the angle is 30 degrees, then this arc out here has to be double that, which is 60. Now if you're going the other way, we have some inscribed angle, it looks like this, and we know this arc is 50 degrees, then the angle has to be half of that. So the angle would have to be 25 degrees. So the angle measure, if we're looking for the angle, take the arc, divide it by 2. If we're looking for the arc, it's 2 times the angle. So if we know the angle, we just multiply it by 2, and that gives us the arc measure. So central angles, same as the angle and the arc are the same. Inscribed angle, the angle is half what the arc is. And this is the one I was talking about. This is what your notes look like. So angle and arc equal to each other for a central angle, or for a central angle. Angle is half the arc. Sorry about that. angle is half the arc for that one. Or you could say that 2 times the angle equals the arc. So if you double the angle, that's going to give you the arc. Sorry, my pen's messing up. Next one, chord angle. Chord angle means you're taking a circle and you're drawing an angle with 2 chords. So we're drawing something like this. We're drawing 2 chords in the circle, and we could be dealing with any of these 4 angles. But you'll notice that these chords cut off an arc here. And if I want to deal with this angle right here, it cuts off this arc. And then on the other side, it cuts off this arc. And we know that these 2 angles are vertical angles, so they have to be the same. So these 2 angles right here are the same. These are 2 arcs that it cuts off. All we do there, when it's a chord angle like this, and it could also be called a secant angle if the lines are extended on out through the circle, is we add the 2 arcs and divide by 2. And that's going to tell us the measure of that angle right there. If we wanted to find this angle, we could add this arc, and divide by 2. The other thing you should realize here, not only are these 2 angles, these 2 vertical angles, so they have to be the same. These 2 are vertical angles, so they have to be the same. And we also know that this angle and this angle should add up to that straight angle, which is 180 degrees. So we know all that stuff. The main thing here, add the 2 arcs, divide by 2, that's going to give you the angle measure. Vertex on a circle. The vertex is on the circle. So we have something like this, a secant tangent angle. We have a secant here. We have a tangent going here. And we're looking for this angle. Notice it cuts off this arc. It's the same as an inscribed angle. The angle is going to be half whatever the arc is. So if we know the arc's 100 degrees, the angle is half that. So that angle right there would have to be 50 degrees. So this is the same. It's always going to be the same as an inscribed angle because the vertex is on the circle. And we're going to talk about more of that here in a second. These are those same 2. So this is that formula. If it's a chord or a secant, then you add the arcs and divide by 2. If it's the vertex is on the circle, like this one, it's just the arc divided by 2. Last thing, if the vertex is outside the circle. So if the vertex of your angle falls somewhere outside the circle. There's 3 different things that could happen. It could be this one, which is a tangent. I'm not sure why I got them in the wrong order here, but this one's a tangent. So you'll notice in a tangent, you have this arc that it cuts off, and then you have this arc. Well, in this one, the 2 arcs together always add up to 360 degrees. So if I know one of them, if I know this one's 100, that means this other one out here has to be 260. And all you do on this one, you take the 2 arcs, 260 minus 100, you subtract the 2 arcs, divide by 2, and that's going to tell you the angle measure. On these other 2, whether it's this one is a secant, but the vertex is outside, so it's not like the other one when we had a secant and the vertex was inside the circle somewhere. This one's outside. You have 2 arcs that it cuts off that's in the angle. Same idea. You're going to subtract the bigger arc minus the smaller arc, divide by 2. Same thing over here, if it's a secant tangent, this is a secant, that's a tangent. A different way that it could be, we had a secant tangent a minute ago that looked something like this. The vertex was on the circle and it came out like this, but the vertex was on the circle, and we just had this one arc that it cut off. This one has two. It has this arc, and it has this arc. All we're going to do here is take the bigger arc, subtract off the smaller arc, and divide by 2, and that's going to tell us the measure of that angle. I know I'm going through this quick, and this is what you have on your paper there. All 3 of these. If you see an angle, looks like any of these 3, where the vertex is outside the circle. Ignore that. Vertex is outside the circle, use that formula. Arc 1 minus arc 2 divided by 2. And when it says arc 1 minus arc 2, what matters, you always want to take the bigger arc minus the smaller arc. If a quadrilateral is inscribed in the circle, we know a quadrilateral is 360 degrees. All the angles, all the interior angles in a quadrilateral have to add up to 360. The other thing that we know using some of this stuff with circles, when it's inscribed in there, these opposite angles, this angle and this angle, have to be supplementary, which means they have to add up to 180 degrees. It works the same for these other 2 angles. Those 2 angles have to add up to 180 degrees. So opposite angles, angles that are across from each other, have to add up to be 180 degrees. If you have any 4-sided figure, it doesn't matter what it looks like, could look like anything, these opposite angles have to add up to 180 degrees. Sector of a circle, talked a little bit, my circle doesn't look much like a circle, but a sector of a circle. So if we have this sector, ignore that extra stuff. If we have this sector, section of a circle, then there's a couple of different things you could do. The arc length, we can find the length of the arc. So we can find this length, like if we were walking around the circle, by using this formula. Arc length equals diameter times pi times the arc measure divided by 360. The arc measure is the degrees. How many degrees the arc is. Sorry about all that. It's how many degrees. Same thing for arc measure down here. If we want the area of the sector, so we're trying to find the area of this piece of pie, we use that formula. I think I got a better slide I'm going to go to. So here we have this. If I'm trying to find, I have some certain section of the circle that I want to deal with here, whatever, that sector. If I want to find the length of this right here, all you're really doing is finding the entire circumference of the circle, finding that entire circumference, and then just taking the part that you want, which is just that part. And that's where the arc measure comes in. So we have arc measure. If this arc measure is 70, we put 70 right here, and we have to find the diameter. Maybe they tell us the radius is 10 or something. Well, diameter is double that, so we put 20 in there, and we do 20 times pi times the arc measure, which is 70, divided by 360. And what that's going to tell us, it's going to tell us the length of that arc. So if we started walking right here and walked to here, it'd tell us how far we walked. Not a whole lot of this on the stuff, and these aren't real hard. If you see a couple of them, you'll think, oh yeah, that makes sense. Area of a sector, so if we wanted to find the area of this piece of pie, we didn't want to find the area of the whole circle, but we wanted just that part of the pi, all you do is you take pi times radius squared, which that's the area of the entire circle. So we find the area of the circle, and then we multiply it by 70 divided by 360. So we're just multiplying it by whatever the area is. Here it'd be, if we use that same circle, it'd be pi times 10 squared times that, and we could plug all that into our calculator, and it would tell us the area of just this piece of the pie, just that section. So just two formulas there. None of these, there's none of them on the homeworks, just stuff that I wanted you to see because we're short on time. This is the page that's probably important, probably the most important. It tells you all the different formulas. This is on the homework. If your vertex is at the center of the circle, the angle and the arc are the same. If the vertex is on the circle, no matter what, if the vertex is on the circle, then the angle equals the arc divided by 2. If the vertex is outside the circle, you subtract the two arcs and divide by 2 to get the angle. If it's inside the circle, we add the two arcs and divide by 2. So if the first one here, vertex is at the center point, the arc and the angle are the same. Second one, the vertex is on the circle, no matter what, if the vertex is on the circle, could be an inscribed angle, could look like that. It could be an angle that looks like that. The angle is half whatever this arc that it cuts off is. Outside the circle, a bunch of different ways it could look, but if the vertex falls outside the circle somehow, so it's out here, you take this arc, the bigger arc, subtract off the smaller arc, divide by 2, and that's going to tell you the angle measure. Again, this is probably the most important thing for the assignment. Inside the circle, so it might look something like this. And I should say inside, not at the center point. If it's at the center point, then we're back up here. But if it's inside, not at the center point, you got an arc here, an arc here. You add them together, divide by 2, and it's going to tell you that angle. And we know that this angle and this angle are the same because they're vertical angles. And we also know that this angle and this angle are supplementary, so we could find all those angles. That's this right here, this page is the key to everything that's going to be on your assignment. This will lead us into the next assignment, which deals with segments and circles. So this deals with segments and circles. If you wanted to stop the video right here and do assignment 14, that's everything that we've learned up to this point, that's what you need. And then you could go back and watch the rest of it for assignment 15, that's fine. I'm going to try to run through it fairly quickly. There's going to be several theorems here, and I didn't write them as theorems on here, I'm just giving you the rules telling them. If you have a picture that looks like this with two tangent segments that go from the same point outside the circle to the circle, they're always going to be congruent to each other. So no matter how you draw this ice cream cone, if you have two tangent segments, no matter what, these two segments always have to be congruent. They always have to be the same length. No matter how it's drawn, you draw something here to here, those two segments are always congruent. Two chords intersect in a circle. If you have this, all this is, it could be set up as a proportion, but this is probably a little easier, so this is the way I set it up. You take this part times this part, and then this part times this part, and those two things have to be equal to each other. So if you know if you know three of the parts, maybe we know this one's 3, this one's 4, this one's 6, and we're looking for this part. Then we do 3 times 6 has to equal 4 times x. And you solve that. It's that simple. This part times this part has to equal this part times that part. Every single time, if it's two chords that intersect inside the circle. Another theorem, two secants intersect outside the circle, so we have a picture that looks like this one. We talked about what the angles and the arcs are, but now we're dealing with the segments. All it is it's this part, segment AB of the top secant here, of this first secant, times the entire thing. Then for the other, and it's equal to this part, the outside part of the second secant, times the entire thing. So the way I wrote it down here, it's exterior part times the whole secant equals exterior part times the whole secant. So if I had some numbers here, maybe this is 7, this is x, we'll say, and this whole thing down here is 12, this whole thing up here is 15. We would do 7 times 15 equals x times that whole thing, which is 12. And you solve that. Where it gets hard, so if you have two secants and they tell you that this part's 8, this part's 10, and they say that this part in here is x, and maybe this whole thing up here is, or they might tell you just the inside part. Maybe the inside part's 12 or something, who knows, doesn't matter. When you do this, you got to make sure it's 8 times the whole thing, which is 20, that's a times, equals the outside part, which is 10, times, here's where it gets hard. That whole thing is 10 plus x. So you'd have to put parentheses there and then work it out that way. Tangent secant, sort of the same thing, except for the tangent, you don't have a part that goes inside the circle. So it's just the tangent times itself. So AB times AB, and then it's the same for the secant. It's the outside part of the secant times the entire length of the whole secant. So if they told you this was 7, and maybe this part was, we'll say x, and this part in here is, from here to here is 5, then we'd have to do something like 7 times 7 equals AC, would just be x, times AD, the whole thing here, would be x plus 5. And we'd have to distribute here, and it's going to give us an x squared, and we'd have to end up dealing with that. And we will talk about how to solve this. I'll do another video that will help with some of this. This goes back to the stuff that you did in algebra, and we'll deal with some of that. Next, if a radius or diameter is perpendicular to a chord, so if you have this chord in a circle and you draw a radius or a diameter to it, and it forms a right angle, then it also bisects the chord. So that means these two parts always have to be congruent. And if that's the case, when we have something like that, notice I have these dotted lines in here. The reason I have those in there is because now we can draw a right triangle on each side, and if we have a right triangle, we can use Pythagorean's theorem and different things. So they tell us that this length is 3, and we knew that this whole chord right here was 8. That means half of it is 4. So now we have this right triangle, and this side's 3, this side's 4, and now all of a sudden we can find the radius of that circle by using Pythagorean's theorem, or if you remember, I made up one that was easy. It's 3, 4, 5, so this side over here, the radius has to be 5. So a main thing here, we have this circle, you have some chord in it, you got some radius that comes down here, forms a right angle, it's always going to bisect it. And then know that you can always draw in that, because that's a radius of the circle. And if I draw in this one, that's a radius, and all these radius of every circle, all radii are congruent. That's another theorem that I didn't put on the notes, but anytime you have a circle, if one radius of that circle is 7, then every other radius is 7. And you can use the right triangle stuff there. Next one. This is a theorem that is based off of that last theorem. If two chords are equidistant from the center point of a circle, then they are congruent. So if I have these two chords, and I know the distance from here to there is the same as the distance from here to there, which these congruent symbols tell me, then I know that this chord, segment BA, has to be the same length as the other chord, segment ES. And not only do I know that, but I also know that these two parts are congruent. And if they're congruent, they're also the same length as these two parts up here. So all 4 of those little parts are the same. And again, I could draw in thing right here, that would be a radius in the circle. And now I have a right triangle, and I can find the radius or any of those other parts if I need to. Didn't realize this had this action on it. Next one, if two chords are equal, then their arcs are equal. Goes sort of along with that. So if I know that this chord is the same length as this chord, then that tells me this arc from here to there, the arc that that chord cuts off, has to be the same as this arc from here to there. So in any circle, if you know two chords are the same length, then the arcs that they cut off have to be the same length. And it works the other way around too. If we know that these two arcs are the same, so they're telling us this arc out here is 72 degrees, if we know that this arc is 72 degrees, then that means these two chords would have to also be the same length. If a regular polygon is inscribed in a circle, the sum of the interior angles, remember we had this formula n minus 2 times 180. So if I have some polygon and it's inscribed in this circle, several things I can do here. If I know that it's regular, that means all these sides are the same. Well, each of those sides is a chord to this circle. So that also tells us that this arc, this arc, this arc, this arc, and this arc are all the same. If I wanted to find that arc right there, all I got to do is know that I'm splitting the circle up into 1, 2, 3, 4, 5. So I could take the whole circle, which is 360, divide by 5. That comes out to be 72. That tells me that arc right there is 72 degrees. Also tells me this arc down here is 72 degrees. Now the other thing you could do is we could find this angle, and we could do it just by using the formulas that we learned. We could take this divided by n if we wanted to find each angle in that. So we could we know that this shape has 1, 2, 3, 4, 5 sides, so we do 5 minus 2 times 180 divided by 5, and that's going to tell us each angle. The other thing that we could do, if you look at this angle right here, it's an inscribed angle, and it cuts off this arc. It goes from here all the way around to here. Well, this arc is 72, this arc here is 72, and this arc here is 72. So if we add all those up, 72 times 3, that's 6, 216. Remember, with an inscribed angle, the angle is half of whatever its arc is, so we just take 216 divided by 2, and we know that that angle right there is 108 degrees. And so is this angle. And so is this angle, so on and so on. And we could do all that stuff with any of this stuff. Main thing here, don't forget those formulas that we learned with polygons. Sorry about all this action, I forgot it was on here. Alright, so if we have this, if we have a circle, and you have a tangent to that circle, so it touches the circle at exactly one point, and you draw, got a circle, you got a tangent to it, and you draw a radius to that point of tangency, it's always going to form a right angle. This angle right here will always be a right angle. So when you draw a radius or a diameter to the point of tangency of a tangent, it's always going to form a right angle. If that's the case, if we have some other point out here, now we can form a right triangle, we can use the trig stuff, we can use Pythagorean's theorem, so on, so on, so on. So a diameter or radius drawn to the point of tangency of a tangent line will always be perpendicular. It will always form a right angle. And the reverse of the converse of that says if we have this and we have this and it forms a right angle there, then we know that this is a tangent line. This one here is pretty important. It's pretty easy, but it's pretty important. If a triangle is inscribed in a semicircle, that means it's inscribed in half of it, then that triangle must have a right angle. It must be a right triangle. So anytime you have a circle, and usually if we were in class, I'd have 5 or 6 of you come up here and do this. If you pick a diameter of the circle and you connect the two endpoints with with the vertex being on the circle, that angle, no matter how somebody draws it, no matter where they draw it to, that angle is always going to be a right angle. So if a triangle is inscribed in a semicircle in half the circle, it's got to be a right triangle. And again, we can use Pythagorean's theorem and the trig stuff all on that. The converse of that says if an inscribed triangle has a diameter as one of its sides, then it must be a right triangle. Circumscribed polygons. Polygons whose sides are tangents to the circles, that's what this looks like. The theorem that goes along with this, since this is a tangent and this is a tangent, and they come from this same point, we know that those two segments have to be the same length. Same thing over here. These two segments have to be the same length. Same thing up here. These two have to be the same length. Same thing over here. These two have to be the same length. So anytime you have some polygon that goes around and its sides are tangents to that circle, these two are the same, these two are the same, these two are the same, these two are the same. It's always got to be that way. Sums of opposite sides, if it's circumscribed, are always equal. So all this is saying is this side plus this side has to equal this side plus this side. That's the end of it. Sorry, it's like 50 minutes long, I know. Again, I'm going to make other videos to try to help you with some of the problems to make sure you understand. I know I'm going through this real quick. There will be a quiz, but the quiz will just be over basic terms to make sure that you sort of watch the video and sort of understand, you know, what a tangent is, what a chord is, so on, so on, so on. But use this video for both assignments.